In general chemistry, when you learned how to draw Lewis structures, you were probably taught how to calculate the formal charge of the atoms in a molecule. In general chemistry, we use formal charge as a tool to help us evaluate the accuracy or the quality of a Lewis structure. We do the same in organic chemistry as well, and we also use formal charge to help us understand reactivity in a molecule. So let's make a note. Formal charge has two purposes. One, it is used to evaluate a Lewis structure, and we'll practice doing that if you can't remember how that's done. And then also, formal charge objective number 2, it is used to help us predict a molecule's reactivity. To calculate the formal charge of an atom in a molecule, we use this equation, the number of valence electrons for the atom minus the number of bonds around the atom and the number of non-bonding electrons around the atom. And when we're doing this, we're looking at the Lewis structure, counting the bonds and the non-bonding electrons. Let's talk a little bit about the valence electrons, the bonds, and the non-bonding electrons. Valence electrons are found on the periodic table, the number of valence electrons. Let's take a look at a periodic table real quick and just refresh how we would use the periodic table to come up with the number of valence electrons. So all of the atoms that are in the first column on the periodic table, they all have one valence electron around them, and all of the atoms on the second column have two valence electrons, and we skip the transition metals. And the next guys over, they have 3 valence electrons, and then 4 and 5 and 6 and 7 and 8. So it's pretty easy to remember because it follows numerical order. And you'll get pretty good at remembering the number of valence electrons for the atoms that we deal with most commonly, like carbon, nitrogen, oxygen, the halogens, and also hydrogen, the ones that we see the most frequently. So the number of valence electrons comes from the periodic table. The number of bonds, that's pretty straightforward. When we're counting the number of bonds, if we have a double bond associated with an atom, it counts as 2. And if we have a triple bond, it counts as 3. And then the number of non-bonding electrons, which we also call lone pairs of electrons around an atom. This is not the number of lone pairs, but the number of electrons themselves. So one lone pair is going to count as 2 electrons, 2 non-bonding electrons. So what I'd like to do is do some examples of calculating formal charges and also remind ourselves about how formal charge is used in terms of evaluating the quality of a Lewis structure, and then also introduce how it's used to predict reactivity. To do this, we are going to start by drawing the Lewis structure of a molecule CH3OH. And we are also going to draw the Lewis structure of a similar molecule, CH3O-. So remember our tricks for drawing Lewis structures of organic molecules. We're going to start by focusing on the atoms that are not hydrogen, so the carbon and the oxygen in this case. And we're going to connect the carbon to the oxygen. There's only one way that we can connect them, which is directly to each other. And once we get those atoms connected, then we are going to fill in the 4 hydrogen atoms, keeping in mind the common bonding patterns that we see for our organic atoms. So carbon likes to form 4 bonds, so we'll give it 3 more hydrogen so that it has 4 bonds. And oxygen likes to form 2 bonds and have 2 lone pairs. So there's the structure of this particular molecule. And let's just go ahead and draw the Lewis structure for the other molecule as well, CH3O-. So for this one, this is a little bit trickier to predict. This molecule just simply has 1 less hydrogen. And so that's what its structure would look like. Now, this is an ion, this is an anion, and in general chemistry, when you were drawing Lewis structures and you were drawing the Lewis structure of a cation or an anion, you probably learned to do something like put brackets around the structure and put the charge in the upper corner, or you may have learned to put a condensed bracket with a charge in the upper corner. We're going to use neither of those strategies in organic chemistry. I will show you what we will use instead to indicate the charge. But let's move on to calculating the formal charges for all of the atoms in this molecule. And let's go back to the CH3OH, and let's begin by calculating the formal charge of carbon. I just chose carbon first. So we have to find the number of valence electrons for carbon. Let's go to our periodic table. We find where carbon is located and what column it's in. That tells us how many valence electrons it has. So we have 4 valence electrons minus how many bonds are around this carbon. 1, 2, 3, 4 bonds. 4. And how many lone pairs of non-bonding electrons do we have? If you look around this carbon atom, it's all bonds, no lone pairs, no non-bonding electrons, so that's a 0. The formal charge for this carbon atom, 4 minus 4 minus 0, is a 0. When an atom has a formal charge of 0, that atom is in an ideal bonding environment, meaning that it has the perfect number of bonds, the perfect number of lone pairs. It's totally happy. And in chemistry, that translates to that particular atom being stable and not reactive. There's nothing wrong with it, so it doesn't have any motivation to try to fix some sort of bad bonding situation. So that's a very stable carbon. And if we look over at our other molecule as well, we're going to see that that carbon is going to have the exact same formal charge. Also has a valence of 4. It also has 4 bonds and no lone pairs. So both of those carbon atoms are going to be perfectly stable. Let's take a look at the hydrogens on the carbons next. We'll do those next. So this particular hydrogen, we'll calculate that one first. First thing we have to do, again, when we're calculating formal charge, we're using this equation up here. Valence electrons, let's look at the periodic table. Hydrogen is in the first column, so it has 1 valence electron. How many bonds are around this hydrogen? Just the 1. And how many non-bonding electrons are around hydrogen? It doesn't have any. So this is 1 minus 0. That's a formal charge of 0. And this hydrogen up here, because it has the same bonding environment, it also has a formal charge of 0. Now remember what that means. That formal charge of 0 means that that hydrogen atom is good. It's happy. It's stable. And what about the rest of the hydrogen atoms in these molecules? They are all, just like the first one that we calculated, they are all a hydrogen with 1 single bond. And always when we have a hydrogen with 1 single bond and no non-bonding electrons, they're all going to have the exact same formal charge of 0 every time. So I'm going to be drawing on, this is getting to be a messy number of arrows. I want to show you something really quick before we get too much further. If we go back a couple of slides and look here, these are bonding trends. We talked about bonding trends. Hydrogen with 1 single bond is a common trend. Why? Because that hydrogen atom has a formal charge of 0. Or a carbon with 4 single bonds is a common trend. Why? Because that carbon has a formal charge of 0. So what we're going to look at next are the oxygen atoms in these two molecules. So I'm going to switch colors here. For this oxygen right here, first thing we need to do is figure out what the number of valence electrons are. Let's go find it on the periodic table. Oxygen is right here, and it has 6 valence electrons. So this is going to be 6 minus how many bonds do we have? 1, 2. minus how many non-bonding electrons do we have? 1, 2, 3, 4. Again, here we're not counting the number of lone pairs, we're counting the number of electrons in lone pairs. So that guy has a formal charge of 0, which means again that this oxygen atom is good. All of the atoms in CH3OH all have a formal charge of 0. We'll come back to that. What about this oxygen atom over here? So this oxygen atom has a different bonding environment. The first one we looked at was 2 single bonds, 2 lone pairs. This is 1 single bond, 3 lone pairs, which means that we don't automatically know that it has a formal charge of 0. Like the other one, we have to calculate it. 6 valence electrons for oxygen minus the 1 bond minus 1, 2, 3, 4, 5, 6 non-bonding electrons. This gives us a formal charge of -1. When we have an atom that has a formal charge, like this oxygen, we will write that formal charge, including its sign, and we will somewhere near the atom, and we will draw a circle around it, which is standard notation in organic chemistry and not used in general chemistry. It's very common for us to draw circles around our charges rather than not, and that's simply just to make them easier for us to find when we're looking at them. Now you know from Gen Chem that when the charge is a -1 or a +1, a lot of times we just write the minus sign rather than writing -1 and draw the charge around it. And there isn't any rule that says that the charge has to be in the upper right-hand corner. We could draw, if we wanted to, we could draw it down here, or we could draw it really anywhere we wanted, as long as we were drawing it somewhere in the vicinity of the oxygen. So what does that mean that this oxygen has a formal charge of -1? It means that this oxygen is unstable. The oxygen is unhappy. There's something wrong with its bonding environment. It makes, the formal charge makes this oxygen atom reactive. It wants to do something to get its formal charge back to 0. So in the CH3OH molecule, where all of the atoms had a formal charge of 0, that tells us that this particular molecule as a whole is pretty stable. Does not do a lot of chemical reactions. But our other molecule, CH3O-, because the molecule has a negative formal charge, the molecule is unstable, it is reactive, it is motivated to try to do something to fix its formal charge. And so not only can we use Lewis structures to predict the reactivity, we can also get real specific about the reactivity. What part of the molecule is reactive? We can figure that out just by looking at the location of the formal charge. The hydrogen atoms and the carbon atom are all happy. They're not reactive. But the oxygen atom is the one that is reactive. So when this CH3O- starts to do some sort of chemical reaction, we're going to see that it's the oxygen atom that's bumping into things and colliding with things and actually initiating some sort of reaction process.